So what about two slit experiments? Well, to do a two slit experiment, well, you see, what we will do is we will imagine that the two slit experiment is done. First, we will imagine that it is done with the particles. Okay, and I'm sure all of you will agree that bullets are particles. We have absolutely no doubt that bullets are particles. So I shall imagine, of course, this is a hypothetical experiment. Nobody who is in the right sense will ever do this experiment. And without doing the experiment, you know exactly what is going to happen. Okay, then so we will imagine that this is first done with particles, and then we will think of what happens if the same experiment is done with waves. There, of course, I mean, you have to do the experiment to get the results, and then finally we will ask what will happen if you do this experiment with electrons or other microscopic things, and the answers are very interesting. So let us imagine that we are going to do this experiment with particles, like bullets. If you want to do a two-slit experiment with the bullets, then obviously you have to have a source of particles, which in this case, of course, would be a gun. So imagine that you have a person who is having a gun, and there are two slits. Here are the two slits, and this person who is carrying the gun, he is going to shoot out bullets. Just to make things interesting, you can imagine that he's drunk, so he is going to shoot out bullets in random directions. And you have these two slits. So what is going to happen is that only some of the bullets will be passing through the two slits. And whenever a bullet passes through a slit, what is going to happen? It is going to be incident upon this wall here, which I am going to refer to as the backstop. And whenever a bullet hits the backstop, it is going to leave a mark on this backstop. And as I said, this is an imaginary experiment or a thought experiment, rather to say. And so therefore, because it is a thought experiment, I can imagine that he is given maybe 100,000 bullets. He shoots out all of them. Maybe 5,000 of them will pass through these two slits and will be hitting the backstop. And so after he has done this, what will I do? As a scientist, I will go and look at the marks that have been made by the bullets at the backstop and plot a graph. That is what scientists would normally do, and plot a graph which shows how these marks are distributed on the backstop. And I shall refer to this as an intensity distribution for the bullets. Okay. So if you did that, what would be the results? Okay, there he is shooting out the bullets, and in fact this figure is taken from that particular website. So here is a schematic arrangement of the results that you will obtain. There are these two slits, and I am going to imagine that only this slit, that is slit number 1, is kept open while the other slit is kept closed. And so what is going to happen is that any bullet that reaches the backstop would have passed through slit number 1. And most of them, what is going to happen is that they will arrive somewhere in this location, somewhere in the vicinity of that point. But it is also possible that a bullet might hit an edge at this location and be deflected, and perhaps once in a while a bullet may arrive at that location also because of deflections. So as you plot the intensity, what are you going to get? You will get a curve which has a maximum like the one that is shown in the figure, and as you go away from the maximum, the intensity will decrease, and I am going to refer to this intensity distribution as I1. Why the subscript 1? Because I am keeping only slit number 1 open. So suppose instead of doing this, I had kept only slit number 2 open. What would be the result? This curve shown with the red color would be the result. And I have called it I2. Okay. Now suppose you do an experiment where both the slits are kept open. Then what is the result? I mean, you don't have to actually do this experiment to say what the result will be. At any point, bullets will be arriving. They might have passed through slit number 1, or they might have passed through slit number 2. If they pass through slit number 1, the intensity distribution is I1, while if they pass through slit number 2, intensity distribution is I2. So I12, right? The intensity distribution in the case where both the slits are open, I will denote it by the symbol I12. And if I wanted to calculate it, what should I do? I will have to take the sum of I1 and I2. So I12 obviously will be the sum of I1 and I2, and that is simple and straightforward. And not only that, you see the bullets have another very interesting characteristic. You see, I will always be getting one bullet or two bullets or three bullets, four bullets and so on. I don't ever get fraction, right? I don't get fraction. So see, the bullets have something which may be referred to as lumpiness, right? If I am doing an experiment, I would have 100 bullets, or the next possible number of bullets is only 102. I don't have 101.5. Okay, I would have 100 bullets and 101, then 102, 103, and so on. So bullets are what I may refer to as lumpiness. That is a characteristic of particles. Okay. Now suppose I did the same kind of experiment with waves. This experiment one can actually perform. How would to perform it? You can imagine that you have a large trough of water here, and I will have something that is vibrating, right? Something that goes up and down on the surface of water, maybe a pencil or something attached to an electromechanical device. The device causes the pencil to vibrate, and as it vibrates, it will penetrate. It cuts the surface of water. So that is my source of waves. And then here I will have a wall which will cut the surface of water, or a board or something which will cut the surface of water. And on that I am going to have two slits, so that the waves that I produce there can pass through these two slits and be detected on the other side. So that is the experimental arrangement that you have to imagine. And what is the result? Well, if you schematically represent it, you see you have the two slits 1 and 2. If I kept only slit number 1 open, what is going to happen? You will get an intensity distribution which may be represented by this green curve called by the name I1. And if you kept only slit number 2 open, what do you get? You will get this curve, red one, denoted by the symbol I2. And the question is, what will happen if you keep both the slits open? In the case of bullets, it was clear that you can get I12 as the sum of I1 and I2, and is that what you are going to get? Well, this is not the result if you are going to do the experiment with waves. The result that you get is not this. You cannot get I12 by adding up I1 with I2, and the actual intensity distribution that you get has a series of maxima and minima. In fact, there are points, for example, a point here or a point there where the intensity is extremely low, close to 0, but there are also points here or there perhaps where the intensity is somewhat large. So you get a series of maxima and minima, and I'm sure you know the reason for this. This is essentially because waves exhibit the phenomenon of interference. Okay, waves exhibit the phenomenon of interference, and that is the reason why this happens. I shall explain this in a little bit more detail. So it is obvious that if I wanted I12, I cannot get it by adding up I1 with I2. And the question is, how will I get I12? If I wanted to calculate I12, what is the thing that I should do? Well, let us imagine that I have only one slit open, and in such a situation, what is the result? Well, I have kept only one slit open, and you can see that the waves are coming out. The waves are coming out through this slit, and they are spreading. And suppose I am sitting here and trying to look at the waves, then I will find that there is some intensity for those waves at that point. And if I wanted to calculate the intensity, I mean, I am not going to go into the details of wave physics, but if I wanted to calculate the intensity roughly, you can say, well, the intensity is actually dependent upon the displacement of the water surface at that point. But displacement, as you know, can be in the upward or in the downward direction. So what would you expect? You would expect that the intensity has to be dependent upon square of the, it has to depend upon the square of the displacement of the water surface at that point. As I said, I am not going to giving you all the details, but roughly speaking, it has to be proportional to the, it has to depend upon the displacement square. It has to be a quadratic involving displacement. So therefore, you see, if I have only slit number 1 open, what should I do? At any particular point, maybe a point here, what I will have to do is I will have to look at the displacement and I will have to think of calculating the intensity using the square of something that is quadratic in the displacement. And that displacement, I am going to denote a displacement. Naturally, you would expect that it should be called a d if I am going to give a notation, but just for the sake of convenience, I am going to call it psi, because eventually psi is going to come into our discussions. So therefore, what will happen is that I will say, okay, I1, why should I put the subscript I1? Because only slit number 1 is open. And if I wanted to calculate the value of I1, what should I do? I will have to find the displacement at any particular point and take its square, calculate its square essentially. I mean, do something with psi square essentially. I shall get the intensity. As I said, this is not the complete description, but this is enough for our purpose. Suppose instead of keeping only slit number 1 open, suppose you had kept slit number 2 open. What would be the result? Well, all that will happen is that in particular point there will be displacement caused by the waves which are passed through this slit, and that displacement I am going to call it psi 2, and naturally the intensity I2 will be dependent upon psi 2 square. Okay, and now suppose I keep both the slits open, right? What is going to happen? Well, if you kept both the slits open, this is how the displacement would be. If you plotted the displacement as a function of position, this is how it is going to be. You can see that, see for example, somewhere here there is hardly any displacement, while somewhere there you will see that there is large displacement, right? Why is it so? The answer is actually extremely simple. I have kept both the slits open. The waves can pass through both the slits. And at any point, what is happening is that there are waves which are passed through slit number 1 and arriving there. There are also waves which are passed through slit number 2 and arriving there. And the net displacement at this location will be due to these two waves. And the displacement due to the first one is psi 1. Displacement due to the second one, let us say it is psi 2. Then what will be the total displacement? Total displacement has to be the sum of these two. So therefore, we have this equation which says that psi 1 2 must be the sum of psi 1 and psi 2, and what can happen is that you see psi 1 and psi 2 may both be in the positive direction, in which case you will have a large displacement. While it may happen that psi 1 and psi 2 may be having opposite signs, in which case they will cancel each other and you will have very small displacement. So that is the reason why you find that you see in these regions in this region or in that region there is hardly any displacement, while in this region there is a fairly large displacement, and therefore what will happen if you look at the intensity as you know is going to be calculated as, or it will depend upon the square of psi. So naturally if psi has a small value, intensity also would have a small value, and that explains how you get this particular interference pattern that we saw earlier. So this is the pattern that you will get. Now suppose you did exactly the same experiment with electrons. So how will you do the experiment? You will imagine that you have an electron gun. So the electron gun is going to shoot to give you electrons. What you will have to do is, I am not going to go into the details of the experiment, but you will have to select electrons, all of which have the same energy, and pass them through an arrangement of two slits, and you will have to detect where they are arriving on a screen. These things can be done these days, there is no problem with that. The only thing is that you see you cannot do it in this room because this room has air. If I produce an electron, the electron will not go anywhere, it will collide with the molecules and will go off somewhere. So you have to do this experiment in ultra high vacuum. And not only that, these days you see you have detectors which are extremely sensitive, they can detect even the arrival of a single electron. Okay. So such an experiment was in fact done. I will give you the details of the experiment in a few minutes. So what you do is you say that okay, this is my source of electrons, these are the two slits, and this is the screen on which I detect the arrival of electrons. If I kept only slit number 1 open, I will get this intensity distribution which I shall refer to as I1. Well, if I kept only slit number 2 open, you will get I2, And in fact, as I told you, it is possible to detect the arrival of electrons one by one if you want. You can actually see where they are arriving, as you will see in a video which I am going to show you. And you find that electrons actually arrive in lumps. You don't get half an electron, you get 1 electron, 2 electrons, 3 electrons, 4 electrons, and so on. So therefore, in that sense, electrons actually resemble bullets, and bullets are particles, right? So they seem to be similar to bullets, and therefore, if I use that and ask the question, what will be I12? I12 is the intensity distribution in the case where I keep both the slits open. What would be the expression for I12? And what would be the answer? Obviously, it has to be the sum of I1 and I2. It has to be. So the expectation is that I12 must be the sum of I1 and I2. But if you actually do the experiment, you don't get the result to be this sum, but what you get is actually an interference pattern. So even though electrons are like bullets, in that they arrive in lumps, the intensity distribution that you experimentally find is not characteristic of particles, but it is characteristic of waves which exhibit interference phenomenon. Okay. So in this case, I1 plus I2 is not equal to I12. But suppose I wanted to calculate I12, what should I do? Well, it means that you see, just like we thought of the wave function, so to say, the wave function in the case of water waves, what was it? It was actually the displacement of the water surface. Just like that, you have to imagine there is something that is associated with the electron, which we will refer to as the wave function and call by the symbol or denote by the symbol psi. What is the use of it? Well, the use is that from it we can calculate the intensity. Okay, number of electrons arriving at a particular location. I can calculate from this psi, and it so happens that in the case of electrons, all that you need is you take the wave function, the psi, and take its square. You will get something that is proportional to the density. Okay, so that is something that you will have to assume. In fact, instead of saying that it is proportional, I have just said that it is equal to, but strictly speaking, it is proportional. Okay, so I12 is the intensity of electrons arriving at different locations on my. When I say intensity of electrons, it essentially means number of electrons arriving per unit area. So I12 we can calculate from a knowledge of the wave function, and it will be, well, strictly, as I said, strictly speaking, there will be a proportionality constant also, but for the sake of simplifying the notation, I have omitted that. So I12 is actually equal to psi12 square. But if you wanted to calculate psi12, what will you do? Just as in the previous case, what you will have to do is you will have to say that psi12 has to have two contributions, one coming from things that have passed through slit number 1 and the other coming from things or waves which have passed through slit number 2, and therefore psi12 must be the sum of psi1 and psi2. So what is I1? We will say that it is contribution to the wave function of the electron from the waves which have passed through slit number 1, and psi2 again similar thing, contribution from the waves which have passed through slit number 2, and these two contributions I have to add together. I am going to get the total wave function, and once I get the total wave function, what should I do? I should take its magnitude and square it. I am going to get the intensity. Okay, this is the address where you should have a look at, and the experiment that was carried out by these people is the one that is shown in this picture. They have a source of electrons which produce mono energetic electrons, that means electrons out of the same energy, and they had a very thin wire. Here is the wire, it is only 1/1000 of a millimeter thick, and the electrons from this source can pass through the left side of the wire or through the right side of the wire. So essentially this is our slit, and they are incident upon a detector. This detector is actually capable of detecting the arrival of a single electron. This was essentially developed by the Hitachi company, and so the experiment was carried out in the Hitachi company in Japan. So what I am going to show you is a video taken from their website, And what you are going to see is the thing that is seen on the screen. On the screen, you will find that bright spots appear. These bright spots, each one of them is a single electron arriving at the screen. Okay.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biprism, thus creating a uniform distribution without any interference when accumulated. Under such condition do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
So therefore, you have seen the video and you can see that this is data from an actual experiment and the interference patterns are clearly visible, and this indicates that electrons do have a wave associated with them. Also, it has shown you that electrons arrive one by one and therefore they resemble bullets, and so they have to be referred to as particles, but these are particles which also have a wave nature. Okay, this is the actual paper in which this data was published. It's of great interest to anybody who is interested in physics, particularly quantum physics. In fact, somebody had put together a list of 10 most interesting experiments ever carried out in physics. A list was prepared, and I think this is actually either number 1 or number 2 in that list. So this is considered to be among the most interesting experiments carried out by physicists, and that is the exact reference. But then you see, you have to notice something that has happened in the video. See, the electrons were actually sent out from the gun under identical conditions. They were all prepared in the same fashion. They were all coming out of the gun. But then when you look at the video screen, what has happened is that they are arriving at different locations. This seems to violate the basic ideas of doing experiments. You see, if you do an experiment, you would expect that the result will always be the same, and this doesn't seem to be happening in this particular experiment, because if I send out one electron, it may arrive somewhere here at the detector, but the next time the electron is arriving somewhere there. The third time the electron is arriving somewhere else. Right? This is as if suppose you are in the chemistry lab doing a titration. The first time you do the titration, you get an answer of maybe 15. Next time you do the experiment, you get an answer of 22.1. And the third time you get an answer of 30.2. And then you would think that, okay, this is not the way science is. The basic idea of science is that experiments repeated again and again should give you the same answer. But here what happens is that when you send out one electron, you cannot say exactly where it is going to be. You can only talk of the probability. See, for example, you have bright regions, and there you can say there is a large probability that the electron will arrive there. You also have darker regions, there you can say, okay, the probability of finding them is small. So here it seems that they can make only probabilistic statements, not exact statements. So then you will ask, in what sense is this particular experiment reproducible? The answer is the following. Suppose you have sent out maybe 100,000 electrons and collected the pattern, then you will get an interference pattern. If somebody else somewhere else in the world does the same experiment with 100,000 electrons and gets the patterns, then your pattern and his pattern will be identical. So therefore, the experiment is reproducible only in that sense. But if you are sending out only one electron, you cannot actually say where it is going to arrive. You can only talk of the probability that it will arrive at a particular location. That you can talk about. Okay. And if you wanted to calculate the probability, what is the procedure that you can adopt? The answer is that you have to go back to your wave function. If you actually wanted to find the probability, you will have to calculate or find the wave function, and you will obviously be able to say that the probability should be proportional to the square of this wave function. Earlier we were saying intensity is proportional to the square of the wave function. We modify that slightly. because we are now thinking of a single electron. And if I am sending out a single electron, I can say, okay, my wave function is going to give me something which is proportional to the probability. That is actually psi square. The wave function square will be proportional to the probability of arriving at any particular location. Now, there were great scientists who were very unhappy with this. You see, they thought that if I send out a single electron, it should be possible for me to say exactly where it arrives. But quantum mechanics does not do that. So, scientists like Einstein were very unhappy about it. In fact, Einstein made a very famous statement. He said that, you see, the way the behavior of an electron is described in quantum mechanics is not completely satisfactory, because you know that if I had a die and if I toss it, then the answer can be any one of the numbers 1 to 6, and nobody can say a priori what the answer will be. You can only talk of the probability that the answer is a 5 or a 6 or a 4 and so on. And he said, you see, in the case of a single electron, if you are sending out a single electron, you are talking only of the probability that the electron will arrive at different locations, and that cannot be correct. And therefore, he made this very famous statement, which is reproduced here: God does not play the game of dice, by which